Hey there. Today we're going to talk about logic gates in kind of a different way, in the way that actually the logic gate is supposed to work. And this is how they do it in electrical engineering. And this is how we're going to understand it much better if you want to understand how exactly logic gates work. So we're going to start with the very basic two operations in logics, and these are the equal operation and the not operation, or the inverse operation. And here we're going to look at what happens if we manipulate A and B. So if we see here A is false and B is false, uh, and when we manipulate or change the values of A and B, or A or B, to true or false, what's going to happen to C value here? And I'm going to take things off the screen so there's no confusion of what we're actually talking about. Yeah. So here we're saying that C equals to A, and now as A is false, there is no signal traveling through to turn C on. So if I turn A on, now the signal is traveling through through A to turn on C. So this mark, that is the two parentheses basically, this item or element is basically saying that it is equal, and we're assigning the value of whatever in A goes straight to C. Now on the opposite side, if we say, well, let's do not. So we're going to say if B is off, and that's the not equal, turn on C. So if B turns on, C goes off. So this sign here, as we use C here, this is a true sign, or a normally open sign, and this is the normally closed sign. So this sign here is true, or passes signal through, when A is true, and this is on when B is actually false. So right now we're looking at B is true, and the signal is off. It's not passing through anything. And if I turn B off, it will pass through a signal to turn C on. If we look at this guy, this is the equal sign, or the assignment sign. Now, this same not operation, we can write it in a little different way. What we're going to do is we're going to do a straight assignment for an input side, and then we're going to say, just like when we say there is C in this line here, we're saying C equals B not. What we can say, and it will give us the same result, we can say that C not equals B. If we turn that on, what's going to happen here is we see that when B is off, C is on. And if I come here and I turn B on, C turns off here. And if we see, it's exactly what's happening right here. So we either say C equals B naught, or we say C naught equals B. Gives us the same kind of result. But this is what we need to understand first. Now, as we understand these main elements, which is the not for the input and not for the output, and the equal for the input and equal for the output, now we can go straight to the logic gates. The logic gates as we know them, these are the AND, OR, NAND, NOR, and their equivalent, and then the XOR. And what we're going to start with is the AND signal, or the AND logic gates. And the AND logic gates is basically two signals in series. Let's call this a signal, or an input signal. If A is on and B is off, the signal is not going through. Just like right now. A is turned on, the signal is going through A. B is off, the signal is not going through B. Now, C will always be off. But then I have to turn B on for C to be on. So now, if we look at the logic gate of AND, we see that the truth table says C is only on when A is on and B is on. So that's when we say C is only true when A and B are true. And this is what is actually happening inside. A signal, A switch needs to be on, B switch needs to be on for the signal to travel between from the input to C, to turn on C. So if I turn off A now, the signal is not traveling through A, regardless. If B is on, whatever B can be, if A is off, C is off. So I cannot have only A, I cannot have only B, I need to have A and B on for the C here to be on. Now that's the AND gate. And to understand it, we look at both A and B as doors. For you to get to C, you need door A to be open, door B to be open. Now, if any of these doors is closed, regardless what happens in the other door, you cannot get to C. So that's the AND gate. Now, as we move on to OR gate, you can see these are in parallel. Door A is in parallel with door B. So now, if I turn door A on, the signal will travel to hit C, or to turn C on. If I turn door B, or signal B on, the signal will travel to turn on C. So now what do I need? To turn on C, I need either one of them or both. So if A is on, C is on. I turn A off, I turn B on. C is on. If they're both on, regardless, the signal is traveling through to turn on C. So this is why we're saying the OR gate, and the truth table of the OR gate, we say that C is on when either A or B is on, That's where we say 1 0 or 0 1, and when both of them are on. And this is the reason why, because the signal is traveling through to get to the C. And if I have both of them in parallel, it can travel through either one of them or both of them. So that's the main idea. Now, looking at the NAND gate. The NAND gate is basically, the way we read it is a negated AND. So you do the AND, whatever logic is the AND gate, which is the series logic that we looked at previously, and then negate that. So it's a negated AND. And we learned up here, we can negate the output or the input. In this case, we negated the output. So if you look at it, it's just like this one, but we negated the output. Now, we've heard of the equivalent of the NAND, and this is basically this guy. So if we take the negation from these guys, or from the output, and take it to the input side, the only difference will be the AND, the series, will be parallel, and then we negate the signals. That's the only thing. So if they're in parallel, they will be in series, and we negate the signals. So we're taking C will be true, will be the normal output, not the negated output, the normal output to C. A and B will be negated, and instead of series, they will be in parallel. And this is where we say not A or not B equals C. Same thing as not C equals A and B, which is basically saying C equals A NAND B, which is basically, it's the negated C. Okay, so this is how we understand it. So we cannot make a mistake in the truth table. Now, when we look at the truth table, we know what's happening. We know that we need a signal. We understand how the circuit looks like and how the signal travels through to turn on C or turn it off, basically. And what we're saying here in this circuit, we're saying if both of them are off, C is on. Why is that? Because of this circuit. You see, the signal is traveling through the off switch when the switch is off. Okay, or the negated switch when the signal is off. So if I turn A on, now it's not traveling through A, but it's still traveling through B. If I turn B on, now it's not traveling through either, it will turn it off. What is happening here is the signal is traveling through both, and it's turned C off. So same result, different approaches, or equivalent approaches, we say. So this is NAND. Same thing we're going to look at, or the kind of the opposite. We're going to look at the NOR. NOR is basically a negated OR. So in this case, we're saying not C equals A or B. Or we can also say it C equals A NOR B. So if we put in a NOT gate here, it will be the NOR. But we wanted to see this can be flipped backward. Now, if we take the negation from here and we put it on the input side, what's going to happen? First, we're going to negate the signals. Second, the parallel becomes series. And that is what we're going to see here. This is good. Signals negated, and they're in series instead of parallel. And this is where we say this is NOR, and this is the equivalent circuit of NOR. That's basically it. And then what is the truth table of NOR? Basically, C can only be true when A and B are false. Because now if I turn any of them on, C will turn off. If I turn both of them on, C will turn off. But I need both of them off so C can be on. And we can see by a circuit why. If you understand it this way, you don't have to remember the truth table. You just have to remember that it is either series or in parallel. Now we're looking at the XOR. The XOR is basically saying A not B or B or not A, B. Okay, so we're going to look at this. So true, false, false, true. If any of these branches, if this branch is true, C will turn on. If this branch is true, C will turn on. Now, how can this branch be true? We know that B is negated, so this switch can be true when B is off or false. This is not a negated switch, so it can be true when A is true. So now if I turn A on, B off, we can travel the signal, we can get the signal to C to turn it on. The opposite is true, right? If I turn B off or B on, A is negated here, so I need it off. B is normal, so I need it on. The signal is traveling here. Can both branches be on at the same time? There's no way. Now, what is the truth table of this XOR gate? Basically, the truth table is saying C can be on if only one of the signals is on. See it? C is on if only one of the signals is on. Not both, if only one of them. Okay? Now, if we look at OR saying C can be on if any of the signal or both of them is on. Okay? But XOR, it's X, true and false. These are false and these are true. That's the X. It's either or. Cannot be true. The XOR cannot be true for C if both signals are on or both signals are off. So basically the whole thing goes back to series or parallel. If we have normal switches, nor normally on switches, in series, that's the AND gate. If normally on switches in series, that's the OR gate. And then we either put in not here or not here. We either put in negation on these guys or no negation on these guys. It's all combinations of these two shapes. Now I can put not B here, and I can put not A here, and it'll be XOR'd, just to prevent C to be on when they're equal, basically. And this is what we see here in the XOR. XOR is basically the OR signal, but we're adding this guy and this guy to prevent it from having equal signals. That's the point. Okay? I hope this helped. I hope you can see how the signal is traveling through the logic gates, and I hope this can give you a little better graphical representation of logic gates. If you have questions, write in the comments and I'll be glad to answer them.